Vincenzo Alba, first lecture.
Okay. So welcome everyone. So before starting, let me thank the people that are organizing this nice school. So it's actually an honor to be here, and it's also nice because it's my first time in Poland. So yeah. So let me start with the introduction. So for those of you who don't know me, so I'm Vincenzo Alba, and I mean, if you have questions or if you want to contact me, you can write to me. So this is my email address. This is a P. Okay, IT. Okay. So let's start with some planning. So what do we want to do in these lectures? Essentially, I want to give you some idea about entanglement dynamics in one-dimensional quantum many-body systems. Okay. So this will be entanglement dynamics in 1D many-body systems. Okay. So there are many words that are important here. Of course, entanglement, 1D. Okay. We will be concerned with the one-dimensional systems. However, okay, our systems are many-body, which means that you have an extensive number of degrees of freedom. Typically, they are strongly interacting. And on top of that, we add another layer of complication because we drive them out of equilibrium, okay? There is a disclaimer that I should make from the very beginning. So not only these models will be 1D, but will be mostly free or integrable, okay? So the reason is that they are interesting on their own. They allow us, they are gentle with us, so we can compute entanglement dynamics exactly in several of these models. They are interesting experimentally, okay? But in order for you not to get the idea that integrable models are the whole world, while doing the calculations, I will explain where integrability enters and what can be different if you consider a generic chaotic model, okay? So the plan is to start with a very minimal introduction about entanglement. In particular, I want to stress I mean, this will be clear in a minute, that entanglement can be seen as a figure of merit of the complexity of a quantum many-body system, okay? And to do that, I will employ the language of matrix product states or tensor networks, which have been already introduced, for instance, in Tomasz lectures, okay? Then, I mean, I will give you some basic facts about out of equilibrium and the idea of equilibration and thermalization, okay? some basic things that I would like to stress. So what is a quantum quench? What is a steady state? How do we describe steady states nowadays? Okay. I hope I can cover these two parts today. Let's see how it goes. Then in, let's say, tomorrow, I'll derive for you, I will introduce the an effective picture for describing entanglement dynamics in integrable models, which goes under the name of quasi-particle picture, okay? QPP, okay? Okay, depending how we'll go, I'll derive for you this this formula, this quasi-particle picture, in the context of conformal field theories, okay? Because this is how the game started, okay? This I cannot, okay, no rise, okay. 4, then the goal is to show that this quasi-particle picture can be used also to describe entanglement dynamics in out-of-equilibrium integrable one-dimensional systems, okay? And in particular here, I'll consider a toy model, okay? Toy model, and this will be something called XX chain, okay? I'll consider a simple quench, actually a quite generic quench in the XX chain, and I will derive for you ab initio the quasi-particle picture. Okay? And last, I write it here, I will present you the conjecture for, sorry, this XX chain is a special case of integrable model, but is a free model, okay? It's a model that can be mapped to free fermions. So it's a particularly simple case of integrable system. Then 5, I'll present a conjecture that is valid for interacting integrable system. For interacting integrable systems, okay? Okay? Okay, so let's see, let's start and see how it goes, okay? So let's start with entanglement. Okay. Okay. So I mean, actually, there are by now there is a large number of reviews that you can look at if you want to learn about entanglement. I like, so there is a special issue of JFISA, which is Calabrese et al., and this is JFISA 42 500 301, I think, something like that. It's a nice collection of reviews on kind of different topics on entanglement. I think it's very nice. So let's start easy. So what is entanglement? Entanglement is somehow a purely quantum correlation which is shared by a subregion with the rest, okay? So in a general setup, you can start with your with your system, and then you can cut a subregion which you might call A, okay? The complement of A, you call it A bar. And then you might ask, so the full system is A plus A bar. And then you might ask, what is the purely quantum correlation which is shared by A and A bar? Okay? Okay? So let us assume, and this is actually very important, that S is in a pure state, okay? So this is the general picture, but however, let's start from the beginning in 1D, okay? So in 1D, we can imagine of having a lattice, okay? Like a lot of lattice models. So these are lattice sites, and then on each of these sites, you can have some quantum degrees of freedom, which can be a fermion or boson, or a spin 1 half, or a generic spin S, okay? Then again, we cut subregion A, okay? And then we have the remainder, which is A bar. So let's start, let's be, very specific, okay? Let's say that this region A contains L sites. This is capital L minus L sites, okay? And let's say that on each site, we have a spin 1 half degree of freedom, okay? And let's say that the full system S is in a pure quantum state, psi. Okay? Now, what I want to do, I want to introduce a representation for this wave function psi. So I want to write psi in the following form. Okay. I write psi equal sum over sigma 1, sigma 2, up to sigma L. Okay. Then I introduce an object which I call T, which carries these indices sigma 1, sigma L. And then here I have my ket, okay? So for spin 1 half, essentially here I'm summing over the possible, so if you want here, sigma I, take the values up and down, okay? And since this is, in general, a non-trivial tensor, okay, this is a non-trivial superposition of spin components, so it's a quantum state. And you can represent any state in this form. It's clear, right? Because, for instance, if you have a singlet, then you have T up equal T down. So if you have two spins, okay, these are 0, and then you have T up down equal minus T down up equal 1 over square root of 2. Okay? Is that clear? This is just a singlet, okay? Up, down, minus down, up over square root of 2. Okay. Now, since we like pictures, because they are useful, not just because we like them. Also because we like them. But so let's introduce a pictorial notation for T. So this T is going to be represented as a blob with some legs, okay? And each leg means represents an index, okay? This index sigma I, which take two values up and down. Okay? So for each choice of this sigma 1, sigma L, here there is a number, a complex number. So you see that you have, this means that to characterize this T, you need two to the L numbers in C, okay? And this, you know, it expresses the complexity of a quantum many-body wave function, okay? As we all know, the complexity in a loose sense, okay, not in a technical sense, of a quantum many-body system grows exponentially with the size, okay, with the number of degrees of freedom. Okay? Now, let us do something, okay? We have this bipartition here, okay? So we can define two orthonormal bases for the two regions, okay? For A, sorry, this is A bar. This is called K, okay? We define two orthonormal bases, okay? So of course this index J and K, I mean, they go, so J goes from 1 up to 2 to the L, and this goes from 1 up to 2 to the L minus L. Okay? Right? Clear? Now you see that we can decompose the state psi as sum over J and K, some matrix J and K, then you have psi I J tensor psi A bar K. We have a basis, we can expand any state in this basis. So we have a basis for A and A bar by tensor product. By taking the tensor product, we have a base for the subsystem. And this is a definition of this MJK. So this is, if you want, is a definition def of MJK. Okay? Given the state, you can define this MJK. You have a matrix MJK. So MJK, in general, okay, is a matrix, is not even square. Okay? Because unless the two subsystems are the same, are equal, or equals of equal sides, these matrices are different. Sorry, this it hasn't. This M is not a square matrix. Now you open Wikipedia, and you look for singular value decomposition. Okay. Then in math books, you find that for any matrix of sides m times n, you can decompose it as U sigma V dagger, okay? Where U is m by m, and V is m by n. And U and V are orthogonal, okay? U dagger is equal identity, V dagger is equal identity, okay? And importantly, so V dagger equal V dagger is equal identity, okay? And importantly, this sigma is diagonal, okay? Actually, the diagonal elements are positive, okay? So in order to highlight this fact, so is actually diagonal square root of lambda 1 square root of lambda up to the largest that you have, okay? Good? Now you see that using this, you can decompose this matrix M. Okay? You can do the SVD of this matrix M. Then this mathematical machinery tell you that this state psi is equal to sum over alpha that goes from, okay, let's call it 10, but then we see what 10 is. Then we have square root of alpha, sorry, square root of lambda alpha. Then you have psi alpha tilde A. So, oops. Tensor product, psi alpha beta tilde. Okay? Okay. And then is the mean between the two dimensions that you have. Okay. So alpha goes from mean 2 to the L to the L minus L. Okay. Now you see we started from sorry, and this V tilde are, sorry, this psi tilde are, so psi tilde A are obtained by applying U to the original basis, okay? And the same for, here I used B, sorry, this is A bar. Okay. Here I have a V dagger, yeah, must be correct, okay? Right? So far, this is just a rewriting, so we didn't gain anything, okay? But so now we have to use a bit of physics. Where is the physics here? The physics is in the scaling, okay? This is just math for now. Physics is in the scaling of the square root of lambda alpha. These are called, sorry, this is called the Schmidt decomposition, and so this was called Schmidt decomposition, and these lambdas are called the Schmidt values, okay? Pictorially, what are we doing pictorially? Pictorially, we are doing this. We are decomposing this tensor, okay, in this way, where this line that connects the two blobs is a name for the index alpha, which is summed over, okay? Okay. But you see, the complexity of these two objects measured in terms of number of complex numbers that you need to know to characterize the tensor didn't change. Now we use the physics. Fact, if lambda alpha decay sufficiently fast, we can imagine of truncating this representation by keeping, let's say, the first chi, the largest, the first chi, okay? We rank them from the largest to the smallest, and then we keep the first chi. Okay, truncating by keeping the chi largest lambda alpha, okay? So the physics is hidden in the properties of this lambda alpha. Depending on the system that you consider, this lambda alpha can decay very fast or can be all of the same order, okay? If you have a product state, it's simple because you have just one of this lambda, which is 1, okay? So I can tell you that, for instance, for ground states of one-dimensional models, okay, usually there is a so-called area law entanglement, which means that there are very few of this. In some sense, very few of these Schmidt values that are important. Okay, you can effectively truncate the representation of the state. So this holds for ground states of local Hamiltonians in 1D at equilibrium. Okay, at 0 temperature. The ground state means at 0 temperature. If you take a system and you drive it out of equilibrium, we'll see that this is actually not true any longer. Now, so this can be thought of as the first step, okay? The first step of a compression. Okay, I use this even though it's wet.
May I ask you, how important is the size of these two, A and A bar, is different? What if?
No, this holds for any case, in any situation. So it can be any. Small l and capital L, there are generic. Actually, you can even do it in the thermodynamic limit if you want. So you can send capital L to infinity, and you can, most of these will be okay. But you see from the math, no? In the Schmidt decomposition, we never used that. This small l and capital L didn't have any particular, didn't play any particular role. Of course.
The lambda, do they depend on the decomposition?
Yeah, of course, yes. In fact, if one subsystem is just one site, you have only two numbers. To appreciate, if you want, the interesting point is that to appreciate how effective is this truncation, better small l and capital L be of the same order, okay? Otherwise, you're doing something a bit, trivial, okay? So, I was saying that this truncation that we started, it's actually the first step of a sequence of truncations that we can make, because you can imagine that we can iterate this, right? So we can iterate. So we go this, okay? We can apply the same machinery to the two blobs, okay? then by keep going, we keep going, and then eventually we end up with this structure. Okay? Okay. This is called the matrix product state. Okay? This is called matrix product state, okay, or for short, MPS.
But is this always possible in the general multipartite case?
What do you mean multipartite? What is always possible is that given a tensor like this, you can always bring it in this form, always.
And does the order of truncations change anything? Or
The order of truncation can, I mean, let's state from the beginning that this is a theory kind of manipulation. Because in order to go from there to there, you need to know this. This means knowing 2 to the L numbers. You don't know 2 to the L numbers if L is too large. So in theory, if you knew this object, you were able to do this. In practice, the way this idea works in numerics is that you postulate that a truncation like this has to be possible, and then variationally, given that you know your Hamiltonian, you fill these tensors, okay? But since you know that this should be possible, then, I mean, so you don't lose anything in representing the state like this, provided that this bond dimension here is large enough. Now, so let's assume that we can truncate, we can do this thing. So for each truncation, we keep the largest chi singular values. How many numbers do we need to describe the state now? So the number, so how many parameters do we need? The number is chi times d times L. Because you know each tensor contains 2 times chi parameters, and then I have L tensors. So, and this, provided that chi doesn't scale exponentially with L, is much less than 2 to the L. Okay? So if chi doesn't scale badly, I mean, we went from an exponential to something that, as a function of L, is linear. This is fixed. Chi-square, sorry. Yeah, chi-square because you have 2 legs, sorry. At the boundary, you have some boundary tensor, but yeah. Okay. Sorry, thanks. Okay? But it doesn't depend dramatically on L, okay? So,
sorry, what is the letter between chi and L? Is it a D?
D, because, sorry, D is, D, yeah, I didn't say, D is the dimension of local Hilbert space. So here I have a spin 1/2, so it's 2. So actually, it's a simple exercise to show that you can write the reduced density matrix for A as sum over alpha, lambda alpha, psi tilde A alpha, psi tilde A bar alpha. Okay? It's a simple exercise. You can do it yourself. Okay? And of course, from the reduced density matrix, you can construct the von Neumann entropy. So for instance, you can construct von Neumann entropy, which is equal to, well, you know by now, minus trace of rho A log rho A. Okay? And this is equal, since here you have already, the reduced density matrix in this representation is diagonal These are orthonormal, blah, blah, blah. This is just minus sum over alpha, lambda alpha, log lambda alpha. So you see? So the singular values are the square roots of the eigenvalues of the reduced density matrix. Okay? Now, what is the largest amount of entanglement that we can have, given that we have a truncation with the chi, with the fixed chi? Okay? So what is? So we have our MPS. So we imagine of cutting, let's say, here. So this is our subsystem A. Now, clearly, let's look at this expression. So the entanglement of A is minus sum over alpha, lambda alpha, log of lambda alpha. Now, the largest amount of entanglement entropy that you can have happens when all these lambdas alpha are equal. Okay? So SA is max. When lambda alpha are equal. And since the density matrix is normalized, they have to be equal to 1 over chi. Because you kept chi singular values, trace of the sum over alpha of lambda alpha has to be 1, so they are all equal to 1 over chi. Then from this you can compute that then SA is log chi. Okay? So you see that the number of parameters that we have to keep to have an efficient MPS representation appears naturally as the largest entanglement that we can have. Okay? So if chi scales polynomially with the subsystem size, with system size, then, I mean, this truncation can be done, if S alpha scales polynomially with sides, it doesn't scale exponentially with size, then you see that you need the chi which grows, let's say, at most polynomially with sides, okay? You don't have an exponential growth, okay? In fact, for one-dimensional systems, this is the largest entanglement that you can have. Okay? Usually you have area law, which means that SA goes to constant. If you have a critical one-dimensional model, then you have a logarithmic violation of the area law, but still you don't have volume law entanglement. Okay? Because something that I should stress, of course, if you have a reduced density matrix, if you take the particularly bad case in which all the eigenvalues are equal, you can have entanglement that grows as volume. Okay? So this is log, area law, and this is called volume law. Okay? You have 2 to the L, 2 to the small l eigenvalues, put them more equal. The entanglement that you get is proportional to L. Okay? So ground states of one-dimensional models, typically they have either this behavior or this behavior if they are critical. Okay? Out of equilibrium, out of equilibrium, the situation is it's very different because at long times you have volume laws. Okay? And the entanglement grows typically linearly with time. Okay? What do we learn from this? So we learn that if we want to have, it's very hard to have an MPS representation of an out of equilibrium state because the number of parameters that we need grows exponentially with time, and in the steady state, it grows exponentially with the subregion size. Okay? So this is in a way in which out of equilibrium systems are much more difficult than equilibrium ones. Okay? At the same time, there are all these parameters that talk to each other. When you have degrees of freedom talk to each other, things kind of become simple because you can use statistical mechanics. Okay? So let me see. I'm going with time. So how much time do I have?
We started late, so 15, 20 minutes.
Okay, great. Okay. I think we are more or less in time. Okay, indeed, now what I want to do is that clear? Is everything clear? Okay. What I want to do is to introduce some, so let's talk about out of equilibrium systems, okay? In particular, let's mention, there are many protocols that you can use. There is a huge variety of out of equilibrium protocols. The one that is quite simple is the quantum quench. Okay, the quantum quench is what we teach to undergrad students, more or less. So we have an initial state. Okay. An initial state, and then we have an Hamiltonian. Let's say that is a time independent. If the Hamiltonian is time independent, things become much more difficult, or maybe simpler. Tomasz is an expert on that also. So, and we do this. So we evolve the state in this way. So e to the minus I ht. H bar is set to 1. Okay. And now, unlike what we do with our master student, with our bachelor students, we start asking deep questions. Okay. No, even with the bachelor students, you ask deep questions. But so let's ask some. This is, why is this important? This is important because, we see that usually we can use statistical mechanics to describe, local degrees of freedom. But if we believe in quantum mechanics, the full system, if you take into account all the degrees of freedom, most likely evolves unitarily. Okay? So the question is how statistical mechanics, so the underlying question is how statistical mechanics emerges from unitary dynamics, okay? What is the problem here? So when we do statistical mechanics, let's say we work with the Gibbs ensemble, okay? So rho Gibbs. Okay? This is a mixed state. Instead, the unitary dynamics will give you always pure states, okay? Because, by definition of unitarity, the definition of state is pure, okay? So how the hell is possible that, we start from a pure state, we end up with a with a description with a mixed state. So the key issue here so the key issue is, so let's say, facts. So fact 1, if we focus on local observables, and I stress local many times, stationary behavior emerges, okay? Point 2, and this is, it means that the system locally equilibrates. So there is local equilibration. Fact 2, stationary state is described by statistical ensembles. Okay, this can be, for instance, the Gibbs. So, and the good thing is that you can actually do, let's say, numerics. You can do ED, okay, or you can do density matrix normalization group. So, okay, you can do your unitary dynamics. You can look at expectation value of the time-dependent expectation value of some local observable. And then typically you see some transient dynamics. But then, if you wait long enough, this expectation value will equilibrate. This is already non-trivial. The even more non-trivial thing is that the final state, the stationary behavior of local observables can be described by Gibbs or variations of the Gibbs ensemble, okay? So let me be precise. So here, because, so let's say that, so because there is an issue which is important with the order of limits. So we say that, an infinite system equilibrates so if for any A, for any subregion, exists the limit t going to infinity, rho A t, okay? And is equal to some rho A of infinity, okay? But the order of limits is important, okay? So you have first to take the thermodynamic limit, okay? V going to infinity first, okay? So when you talk about equilibration or thermalization, you need to be in the thermodynamic limit. Okay? So you have a full system, okay, which is evolving, okay? Then you consider a small region A of size L, okay? So the ratio small l over capital L is 0 because you are in the thermodynamic limit. And then you send t to infinity, okay? This is the notion of equilibration, okay? You can consider different limits, okay? You can take t going to infinity with finite capital L. You can study it, it's interesting. There are many questions that you can ask. But This is kind of the simpler and the one we are used to from statistical mechanics. Okay. Okay, so we're almost there. So I was mentioning that typically what you get is that the rho of equilibration is 1 over z e to the minus beta h. Okay, so it's the Gibbs ensemble. Okay, where beta is inverse temperature. Okay, this means that all local properties of the system in the t equal infinity limit can be described by this. Okay, this means that trace over A of some observable which has support in A from t going to infinity is equal to trace of rho equilibration, which means Gibbs of O. Okay. Okay, and the beta that you have to choose is the beta that corresponds to the initial energy density. Okay, the energy is preserved during the dynamics, so you can fix beta by fixing the expectation value of the energy over the ensemble, of the Hamiltonian over the ensemble. Okay, and then automatically you fix the expectation value of all the local observables. Okay, and you see that. Here is the first time where we encounter this simplification. Okay, so this how to say this fact that even though we have a humongous number of degrees of freedom which are strongly interacting, entanglement grows linearly, it saturates the volume law, and then in the steady state we need just one parameter to describe any local observable, which is the inverse temperature. Okay, it's just one parameter. Okay, when does this work? This works for typical Hamiltonians, okay, which means, whatever that means, chaotic Hamiltonians, okay, in which you don't have other conserved quantities except for the energy, okay?
Is it possible to have a non-equilibrium stationary state for a chaotic one-path Hamiltonian?
Non-equilibrium stationary state? I mean, as I told you, so the system typically reaches a steady state, and then the steady state is described by some Gibbs density matrix. Okay?
But,
what do you mean non-equilibrium then? Yeah. You mean something that is described by not by the Gibbs ensemble?
Yeah, but it's still like some currents or something.
No, some currents, I think it's, unless you put some boundary driving stuff like that, no. But, sorry?
So this, the psi naught, is it like an eigenstate of the H naught, not H, huh?
Sorry, this, yeah, I didn't say. So for this to be non-trivial, psi naught has to be not an eigenstate of H. Otherwise, this would not evolve. So this psi naught,
No, psi naught is an eigenstate of H naught, right?
You can have an H naught and then you can imagine of changing H naught to H suddenly. But you can just say that you prepare an arbitrary state and you evolve with the given Hamiltonian. Okay? You don't need to prepare the initial state, as a ground state of another Hamiltonian. You can just, let's say you have access with your experiment to the local degrees of freedom. You can arrange the local degrees of freedom the way you want. Okay?
So these Hamiltonians can be gapped or gapless, that doesn't matter.
Gaplessness here doesn't play any role because usually the energy density that you have in the system is, usually you pump an extensive amount of energy in the system. So the expectation value of the Hamiltonian over the initial state, which is preserved, is very far from the ground state energy. Okay? So indeed, typically non-trivial out of equilibrium dynamics happen in the middle of the spectrum. Okay? So the eigenstates that play a significant role are eigenstates in the middle of the spectrum. Hence the fact that thermalization, ETH, eigenstate thermalization important is crucial. Okay. Okay. So, this equilibration to Gibbs holds only for chaotic Hamiltonians. Okay. However, here we want to work with integrable systems. So here we want to deal with integrability, and a way of saying that a system is integrable is by saying that it has an extensive number of conserved quantities, okay? You have a set of operators I,N, which are local or quasi-local, okay? Local or quasi-local, and both these adjectives are important, okay? They commute with themselves, okay? One of these you can call it Hamiltonian, okay? And there is an extensive number of them, okay? Okay, it's crucial that these quantities are local or quasi-local, because otherwise you might say that any quantum system is integrable, because if you have an Hamiltonian, then you take the projectors over the eigenstates. These are conserved, but they apparently don't play any role in the dynamics, and this is the case because they are not local typically, okay? Right? Okay? Now, what are the consequences of this fact? The consequences of this fact are that now, during the dynamics, the energy is preserved, but also the expectation values of any of these quantities preserved, okay? This means that one parameter, namely inverse temperature or mean energy density, is not enough cannot be enough to describe the steady state. And what you can do is, this is a very long story. How much time?
4 minutes.
4 minutes, okay. Yeah, I think it's enough. So, something that has been discovered in the last, let's say, 20 years is that to describe the steady state, in integrable dynamics, you can use something called the generalized Gibbs ensemble. Okay, and this is, I mean, it's a GGE, and the density matrix of a GG is defined as sum over M over some normalization. Okay, so you have an extensive number of parameters lambda m, which are Lagrange multipliers, and they are fixed by requiring that trace over em rho GGE is equal to the expectation value of the charge. Okay, so by fixing all this an extensive number of expectation values, at least in principle, you can fix the Lagrange multipliers. Okay, this program in practice cannot be done. There are more efficient ways of defining the GG. Okay, so I think I can stop more or less. But the last thing that I want to say is that so something that I would like to stress is that what happens both for integrable and non-integrable systems is that there is out of equilibrium dynamics. What happens is that there is local equilibration, which means that locally the system becomes describable by a statistical ensemble, which is what we learn. I mean, looks kind of classical, but this fact, as the system locally approaches the statistical ensemble, what happens is that the system at the same time is building strong entanglement with the, so the subsystem A is building strong entanglement with the remainder. Okay, so this the process of equilibration and also thermalization is very deeply intertwined with the growth of entanglement. Okay, while you are becoming while the system is becoming describable by statistical mechanics, at the same time is building strong quantum correlation, okay, between distant degrees of freedom. Okay, and I mean today we stop here, but tomorrow and the next days we'll see more in detail how this happens. Okay, thanks.
One question.
Yeah.
So is it possible to write such kind of typicality argument for integrable systems using the generalized Gibbs ensemble?
I mean, this is what I wanted to finish with today, and I didn't manage. Tomorrow I'll start by mentioning that. Okay? I mean, I can just mention it, but I can say what is the role of ETH in this business. Okay? There is ETH, and I really would like to stress that there is a weak sense in which ETH holds also for integrable systems. Because you have an extensive number of degrees of freedom, you have an extensive number of conserved quantities, but you have an exponentially number of eigenstates in each microangular window that you can have. Okay, so and this means that there is a version of ETH also. Yeah. Okay.
And maybe one more question. So when you say thermalization, you mean that the late time value is given by the Gibbs ensemble?
This was my intention. I think I failed because I didn't stress hard enough. Yeah, but yes, thermalization for me means that in the end you get the Gibbs ensemble. Otherwise, you equilibrate to a GG. Okay. I mean, there are also situations in which you don't equilibrate. Okay, you can invent states, initial states that prevent you from reaching equilibration. Okay, so you can invent. Okay. Yep.
So for VDATH, is it known how much sub-extensive can you be from the number of conserved quantities?
I mean, let me anticipate what I'm going to say tomorrow. Even in integrable systems, let's say that you do the experiment, you have the spectrum of integrable system in front of you, you pick a macroeconomical window, given corresponding to a certain energy. If you pick a random eigenstates in that window. With the probability almost 1, that state would be thermal at that temperature. So the vast majority of eigenstates in energy window, in a macroeconomic energy window, even for integrable models, is thermal. But at the same time, there is an exponentially large number of states which are not the eigenstates that are non-thermal. Okay? The ratio between the number of eigenstates that are thermal the ratio between the number of states that are non-thermal over the number of states that are thermal in the thermodynamic limit goes to 0. But, okay? Because the entropy of a thermal state is larger, almost by definition, as compared to the thermal of to the entropy of a non-thermal state. Okay? This is the summary of what I'm going to say tomorrow. Okay? No, it's essentially what I'm going to say tomorrow.
For square root n conserved quantity, will you still get weak ETH?
I mean, I don't know if there is a model where you can play, where you can tune the number of this. I don't know. I mean, no, I don't know. I mean, these statements, the statements about ETH are, I mean, based on experience and conjectures and on numerical studies in integrable systems, because there are effective ways in integrable system to probe ETH using integrability. But then what happens if you, so you're asking how the number of non-thermal states scales with the number of conserved quantities. Yeah, it's a very tough question. Yeah.
If there are no other questions, let's thank Vincenzo again. And